before I forget. We're recording. All right, cool. So a couple of things I wanted to talk about before we get started today. Uh, first and foremost, it's raining pretty hard here. Well, not hard, but it's pretty like I don't know. They warned me of like severe thunderstorms. So if everything just all of a sudden shuts off, just don't freak out. I don't know. I don't know what to really do in that situation because I'm pretty sure then my Wi-Fi is going to go out and then the meeting would get canceled, right? So we'll let's hope that doesn't happen. But yeah, welcome everyone. I hope you guys are doing well. We are really just in the middle of it all right now. We're approaching like the halfway point. All right. Your midterm, I forgot to write it down, but your midterm is coming up. It's on Wednesday. All right. So the way it kind of just fell, the stuff we're going to do on Monday will not be on your midterm Wednesday. So the things that we're going to do today it's pretty much like the last thing we're going to cover. And then like everything from before is going to be on the midterm, if that makes sense. Okay. And then afterwards, so the stuff from Monday on will be on your final. Okay. So I'm not going to put stuff from the beginning of the course on the final. It's just cut in two halves this year. All right. So once again, your midterm's on Wednesday, and the stuff on Monday will not be on your midterm. Okay. That doesn't mean like you can kind of blow off Monday. It's gonna come back. All right. The stuff on Monday is actually going to be on your next quiz, which is your next quiz is on the 21st. So you got some time for that. All right. Usually like I give a second quiz like after the midterm or be right before the midterm, but things got cut and whatever. So
someone asked something on the chat.
Oh.
I think they're asking if the midterm is going to be during class.
Yeah, so our midterm is on Wednesday. So like, right? Yeah, our midterm is on Wednesday. So the whole class is just going to be you guys taking a midterm and me watching you guys take a midterm. Right? Any other questions about the midterm? I mean, there should be like sufficient time. There should be sufficient time for you guys to like cover those stuff on the midterm. I think I even dedicated like part of the recitation, your next recitation, to that. All right, so I'm gonna ask China to go over the stuff that we covered today, but not the stuff that we cover. Not so much the stuff we cover on Monday, so that you guys can like review a little bit more for the midterm, right? Quiz. Okay, so there were some issues that came up with the quiz. Some people had issues like with submissions. Some people didn't upload on time. I had warned you guys, or not warned, but I told you guys that after the quiz, I would give a 10-minute period for uploading. That 10 minutes was not for you to finish your quiz. It was just for you to upload. So if you were unable to upload, I should give you a 0. That's how it should be. Okay. I understand, like I'm going to be lenient, this time around. Some people like reached out to China or myself and we got it all figured out. That's great. And I'm going to be flexible with that. But I'm just letting you know, in the fall, I don't know, like you might get like one of those crabby old like professors and like who's not like, as, nice like us, so just be on the lookout for that, and this kind of like goes in my next point. Like, I feel like there needs to be proper online like etiquette, if that makes sense. Things that like, I don't know, I feel like I shouldn't have to say, but I guess I do have to say just to make sure that I'm covering all the bases here. Things like one, being on time, right? Like being on time doesn't mean getting to class, like getting to 110 class at 110, right? Being on time means getting to 110 class at 1 or like 105 the latest, so you can settle down, get ready, get started, right? Things like emails, like so far the emails have been great. They've been very professional, but then things like responding. So let's say a student emails me something and I email back, you should email me back to confirm that either you got it or like, okay, I understand. You shouldn't assume that like, oh, like he understands. You know, like it needs to be clear, especially like online. So please like work on that etiquette. I know some of you are still kind of getting adjusted to this, so it's fine. But and then of course, lastly, submitting your work, making sure your work is like properly submitted. If you're running into issues, you have to let the professor know. You can't just like submit it super late and then like with like and like not explain yourself and then like just assume that they understand what happened. You need to like advocate for yourself. I kind of like said that in the beginning of the year too, or beginning of this thing too. All right. Sorry, I don't mean to like lecture you guys on that stuff, but like you guys like gotta understand that you're not in high school anymore, right? Like you made this choice to go into college. You were chosen for this program. We have higher standards for you. We as in like us and Rutgers, overall, So just make sure you're on top of your stuff a little bit more with that stuff. And of course, if you run into any issues, this is why we kind of like really, really harp on you guys. Just let us know. Like, don't like say nothing. Like, let someone know so that we can kind of like be like, oh yeah, that student told me that blah 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 blah. They're okay. So yeah, we got to work on this communication a little bit better. Hopefully that does get better over the next, what is this, 6 lectures, 7 lectures, 6 lectures. Yeah. Oh my gosh, we're like pretty much halfway through, guys. So yeah. Okay, that was my little spiel. Quiz. The quiz was okay. Like, was there anything on there that was like, what the heck? John did not teach us.
Wait, I have a question.
Oh yeah, what's up, Mom?
Yeah, so me and Shuban, since we had our graduation, we missed the quiz. So
Is Shuban here? I read
Yeah.
here because I
I,
actually wanted to talk with you guys. Thanks for reminding me. Actually, Shuban, I sent you a message on GroupMe. I don't know if you got it, but
John Alvaro also said he missed a quiz in the chat.
Alvaro was excused. So like, okay, so when a student misses a class, right? We are notified. The staff is notified that the student is like not going to be there for whatever reason. But for Shuban, I didn't get an email. So, and I don't think Dean Brown knows. So I don't know if I can give you a makeup. You gotta clear that up with Dean Brown.
yeah, that's why I took the quiz in class.
Okay, so now you're telling me a different story. So I don't know what to think, because
No. So what happened was I emailed Dean Brown saying that I will miss the first 2 classes. That's why, and then I think he never so he didn't knew that I'm gonna miss first portion of calc.
okay,
So I was outside for my graduation, and then I missed first few minutes for class, but I did get to take the test.
okay, all right then. Shubhan, it sounds like you're good then, right?
Yeah.
Then Mohammed. So whoever else missed it, I think it's Mohammed and
wait, were you notified for my one?
Alvaro. Yeah. Well, late. I was notified late about
Okay.
but because apparently your graduation was like pushed or something like that.
Yeah, it was supposed to be because it was supposed to
Yeah.
be Wednesday, and they literally changed it last minute because of the rain date.
Yeah.
So
Okay.
and they were letting us know that it's
So
like
if
yeah.
It was
okay, so
supposed
this
to be Wednesday evening.
yeah,
Yeah.
okay, it's fine. So this is kind of going back to the whole like being responsible and like online etiquette and all that stuff. Like if you missed a quiz, you have to set. It's your responsibility to set up like a time to like retake it or something, because it's not like high school. The teacher's not going to chase you down anymore. If you miss the quiz and you don't like explain yourself, or like if you don't like set something up or whatever, like we're just gonna give you the 0. That's just how it works. Like we're not going to chase you down. All right. So I really hope you guys emailed China, because I didn't get anything from you guys. So I don't know what the plan is here. Did you guys email China? I hope you did.
I haven't sent the email yet, but I was
Oh my
thinking of
gosh.
doing it during tutoring or like
Okay, no,
before class.
you need to. If you guys knew that you weren't going to be there, you should have emailed her like yesterday or like the day before. Okay, so you guys are super late right now. So right after this class or right after orientation, engineering orientation, shoot the email like right away. All right, say like, hey, can we set up a time to blah 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 blah. All right, so like I said, you got to be responsible for your stuff. All right. Okay. Oh my gosh, I'm wasting so much time here. So the quiz though, how was it for everyone else that took it and submitted it? It was like fair, I hope. Everything that I said was wasn't too bad. It was time that made me nervous. As time went down, the more I panicked. Yeah. All right. It sounds a lot like the pretest, right? So yeah, you guys now know how the quizzes are formatted. You guys now know like what to expect, right? I pretty much tell you guys everything that's on there. I don't like to give like too many curveballs. You might get one in the midterm, but you guys now have a taste of what the assessments are going to be like. Okay, so yeah, just remember that for the next one.
I was gonna say something.
Who's talking?
Shubhan.
Oh yeah, what's up, Shubham?
Yeah, so I took the test yesterday, right? And then while submitting it, it took me about 6 minutes to load the answers. Like when I tried to submit it, it took me about 6 minutes. So it was like 2:16 when I submitted my work.
Yeah, yeah. I intentionally gave everyone an extra 10 minutes at the end. So
Okay.
the due date, the due time was not 2:10. The due time was 2:20, so that 10 minutes you guys had to kind of upload or scan or whatever you had to do. That's the whole point of the 10 minutes. Did you guys read the instructions?
Yeah, I read it, but
Okay.
then you said not you know how you said you're not supposed to write the answers during the last 10 minutes. So I'm just making sure that.
Yeah. That's fine. It's okay. As long as you got it in before 2:20, it's fine. All right.
Okay.
I'm reading the comments. 10 quiz. Yeah, I know. I guess yeah. Distractions at home. Quiz was fair. Quiz car AP exam. Really? It did? That's interesting. All right. But okay. All right. Overall, I'm seeing that the quiz was fair. I also read through some of the responses on that survey I sent. Some of you still haven't done it. It's okay. Whatever. At this point, I kind of have a general feel of what's going on. I read through the responses. Most of them were good. Most of them made me feel really good. Because like a lot of them were just kind of like, oh, we're doing fine. Like, thanks for the videos and yada yada yada. So, but if your honest opinion is, John, like I can't do this, like then you gotta let me know, all right, for whatever reason. So we can kind of adjust. All right. So, whoops, that's the highlighter. So quiz was okay. Know your next quiz, know your next midterm, right? Dates, and then the homework for. It's kind of weird because usually you have 3 recitations in a week, but this year they're not doing that. So the homework for today and Monday will be due Thursday. Yes. Yeah. Because the homework that was given on yesterday is going to be due Tuesday, right? Did I get that right? We go from recitation to recitation, so remember your homework dates. I wanted to start today with clearing up some stuff from 9-4. There was some. Yeah, sure, Harry. Just stick around, okay? So I wanted to go over something that I kind of like blew past, and it shouldn't have affected your quiz results, but it does affect the conceptual part of logistic growth. So I wanted to talk about that real quick. We are going to skip 11.1 and 11.2. That is the parametric stuff. I had to decide something to cut this year, and we just decided parametric just because it's not as prevalent. It kind of is important, but it's not as prevalent as polar coordinates. So I decided to talk more about polar coordinates. I hope that's okay. And also polar coordinates, they come up a lot more in like Calc 3 and like later calcs and stuff like that. Okay. So let's get to it.
Hey John, sorry, really quickly.
Yeah.
Yesterday, China, she didn't tell us that we had homework. So where is it? I just checked Canvas and I can't find it.
She's responsible for that homework stuff, so I would reach out to her, be like, "Oh, do we have homework, or what was our homework, or whatever." I guess because of the quiz, maybe she forgot or something, or But yeah, definitely reach out to her. She should be able to,
All right,
or
thanks.
she might post it later.
Okay.
Okay. Logistic growth. So I wanted to talk about a couple quick things about logistic growth first. Do you guys remember we defined K as the oh my gosh, growth constant last class, right? It actually kind of depends on which like form you're using. What do I mean by that? So like, let's say I'm gonna do this all in one fell swoop. Let's say I give you this example right here. dp over dt is equal to p over 5, 1 minus p over 12. I had mentioned last class that there were like two like forms of logistic growth that kind of come up. I'll title this one like the BC version, and this one is like the book version. The BC version is dp over dt. This is the one I taught. And actually it's the one that I'm more familiar with. Well, the book version is this one. And it goes 1 minus p over m. I'm just trying to keep the variables consistent. All right. So with the book version, all right, the k value is not this ends up not being the same as the k value in the BC version. So to kind of help with this, I'm gonna like call this one K1 and then call this one K2. Okay. The growth constant is the same. Like overall, it should be the same for both, but the k value may not be. So it's like I'm trying to say the k value is like defined as a growth constant, but like what specific growth constant? It's like not it's not as explicit in the textbook. So like let's say in this problem, right? So for this problem, the book would define, since this is in the book form, right? The book would define the k value as 1/5. So in this case, K2 is 1/5. All right, I'm just gonna look around. Are you guys still with me here? Maybe?
Yeah.
Hold on. So if I were to change this into the BC version, right? I would have to factor out the 112. So I would get p over 5 times 112 is 12 minus p, right? So in this case, right, this is the BC version. In this case, you see that the k value is actually different, right? If I multiply the 1/5 and the 112, I actually end up getting p over 60, 12 minus p, right? So in this problem, in this context, the k value is actually 1 over 60. So it's like, does that mean the growth constant is different? No, it kind of depends on how you define growth constant in the context of your problem. I really hope that made sense, because I know it's a little confusing.
Yeah, it did.
Anyone have any questions on that? So this should explain, if you guys watch the video, my supplementary video, this should explain why my answer was different from the book answer. Because in that problem, they defined k in like using this form. You know what I mean? So I think my answer was like off by like a factor of 1,000, but it's because like, you know, I factored out like 1 over 1,000 and things like that. All right, so definitely check out the video if you haven't already. But hopefully this clears things up.
So John, in the fall, they're gonna use the K2 version?
I believe so. I believe they use that a lot more. It's like, it's kind of like, you know, why do we have different forms of like, you know, the same equation? It depends on the situation. You know, sometimes it's easier to use the book version. Sometimes it's easier to use the like BC version. To me, the BC version is easier to understand than the book version. And then the book, I think the book version is like, might be more practical than the BC version. So, but that's like the user's like choice, you know, it's like, it's up to them.
Yeah, okay,
Right?
thank you.
Yeah. So like I said, be on the lookout for both of these. And yes, both of these end up like getting different particular solutions. I think I gave those to you guys last lecture too, right? So that was my little clear up with 9.4. Can someone remind me, did I talk about like when the graph is going the fastest last class or no? Did we talk
I
about that?
don't believe so. We didn't
You
talk
said like
about
the middle of the graph, right? Where you
Oh
asked.
yeah, yeah,
Oh,
yeah,
yeah.
yeah.
Oh yeah,
Okay.
yeah, yeah.
Cool. So like, okay, so like with this example, I'll rewrite the example again. Is equal to, I'll write it in this one. So if I were to ask you guys for what p-value is the graph moving the fastest, like what would you guys say?
when P equals 1.
So I'm saying at what population value is the graph P of t moving the fastest?
At
Remember,
1.
it's not one. So remember, all logistic graphs look like this, right? This would be my P of t, my population function, right? Like if I integrated this, separated the variables, yada, 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 I would get a particular solution, P of t, right? I'm saying for what P of t value, for what P value would be the graph, would the graph be moving the fastest? Okay, I'll give you guys a hint. What is this value?
The carrying capacity.
Yeah, the carrying capacity. Remember, the carrying capacity is like, it's like an asymptote. The P of t graph's going to get really, really close to it, right? Well, if that's the top, then where's half of it?
Then it's divided by 2. I'm divided by.
So what? So okay, so we got to figure out what is the carrying capacity.
So
Do
okay,
6.
The carrying capacity is 12, right? Meaning the halfway point is 6. You guys see that?
Yes,
Notice
sir.
I didn't have to integrate. I didn't have to like separate the variables. All I had to do was identify my m, right? And just take half of it. Is that all right? That was a really long silence. So
Makes
I'm
sense.
worried now. So that means, right? If I wanted to find the time, what would I do then? The time at which that happens.
You just plug it in.
What is that? Don't be so generic. Like plug what in?
Wouldn't
Plug
you
my
create
Febreze thing into the outlet?
Yeah.
I would do that.
Plug what in where? Plug.
Wouldn't you use the general formula and plug in the m and the growth factor and set it equal to 12?
Right.
I mean,
so you would have to find P of t first, and then set P of t equal to 6. Solve for t. Yeah. And I kind of did an example like that in the supplementary video. So definitely check that out if you haven't. Look through the examples in the section if you want to. Right. All right. Oh my gosh, that kind of took a long time. So we're done with that. We're gonna shift gears now. We are skipping chapter 10, which chapter 10 kind of talks about series. So we're gonna come back to that after this, right? So we're gonna go on to chapter 11, which is on parametric, but I said we're gonna skip that. It's on like arc length, which I'm kind of gonna skip with the parametric stuff, and then in 11.3, they start with polar coordinates. All right, 6:53. You guys ready for polar?
Yeah.
So polar coordinates. What are polar coordinates? It's just a different like type of way to graph functions. I'm sorry, I shouldn't use the word functions because polar graphs, they all failed the vertical line test. So they are a different way to define functions. I know you guys are used to defining functions as like x input, y output, but with polar coordinates, the inputs are actually theta values. All right. And oh, I'm sorry, I should write F. Right. It's the inputs are theta into your function, and you output an R value. So theta represents an angle. Like you guys should know how to measure angles on the coordinate plane already, right? When you guys did trig. And R stands for a radial length. Okay, so theta is an angle, R is a radial length. So it's like if I wanted to get to a certain point on the coordinate plane, right? So it's like, I think a really common misconception with polar coordinates is that like, oh, it's a brand new plane, but it's actually not. It's actually, we are still on the XY plane. We're just getting to our points differently, right? I'm not shifting like left, right, like up, down anymore. I'm actually going to go a certain theta amount, and then like from the origin, I should add that actually. Oops, radial length from the origin. So from the origin, we kind of go out a certain distance depending on where our theta value is, right? So that would be my radial length. Right, and with this kind of approach, we can actually get anywhere on the XY plane, right? Which is why we play on the XY plane. How are we doing? Does it make sense?
Yeah.
I know polar coordinates probably was skipped this year, for obvious reasons, because it wasn't on the BC exam. So BC kids probably aren't as familiar. And then for the rest of you guys, I think the last time you saw polar coordinates was probably like pre-calc, maybe. Like I know like some schools do it, some schools don't. So I understand this is brand new stuff. So please like slow me down, stop me if you have to. Be like, John, can you just explain that again? And I will, okay? All right. So that's what kind of polar coordinates are. And like I said, we can get to any point we want on the XY plane just using a certain angle measurement and a certain R length, okay? So why don't we,
Wait, John.
why don't we do, yeah.
So the theta value will determine, it'll sort of determine the position on both the X and Y, but the R, the radial length, is determined by the function.
Yes, whatever your function. So your function is going to be like, you know how like functions, you're used to seeing functions in terms of X? They're going to be in terms of theta now. So you input an angle and it'll output a radial length. So I think a good example is like kind of like can you guys imagine like a cannon, right?
Yeah.
So how you like arc the cannon determines the angle, right? I mean, represents the angle, and then how much like I guess gunpowder is in it will determine how far it goes. Does that make sense? So
Yeah.
that's kind of like the idea. It's not, like I said, it's not left, right, up, down movements anymore. It's like sweeping movements. Like I'm gonna go a certain amount here and then pew, like shoot out a certain like radial length. Is that all right?
Yeah.
So then all the points in a function will follow that?
Yes. And what ends up happening is it produces different looking functions that look pretty trippy actually. But anyways, so I'll get to that in a second. So the last thing I want to talk about, oh, okay. So that means you guys are familiar with negative theta values, right? Like what does that mean?
You basically do go reverse. If you
what
understand what I'm
direction
trying
is
to say.
reverse?
You go clockwise on the
Yeah, clockwise.
line.
So negative theta values is going to be clockwise, but then what are negative R values?
It is gonna be It's gonna. I don't want to say reverse. I say reverse, but like yeah.
Okay, reverse, but what does that mean? Like if I'm talking about the radial length.
You know, I don't know the word for it, but you know how right now it's coming from like the origin to like the top right? It's just gonna go to the bottom left.
Good. Yeah. It just goes in the opposite direction. So like if I said, I'll call this example 1. If I said plot, so it always goes R theta. Like I don't know why it does it in that order. It should make more sense to go theta R because it goes input output, but usually it goes R theta. So if I said negative 5 comma pi over 4. So like you guys are used to seeing like x comma y, right? And seeing like, like if I say 4, 7, right? That means go right 4, up 7. Well, if I have something like -5 comma pi over 4, right? Well, that means -5 is determined by the pi over 4. So I need to go pi over 4 first, which is 45 degrees, if you don't remember, right? So that's 45 degrees. But then a -5, right? A distance of 5 in the negative direction tells me to go here, right? So this point is -5 comma pi over 4.
Do you draw like the line too?
No, you don't have to. You don't have to. I was just doing that to kind of show you guys like that you're shooting in the other direction. How are we doing? Am I going too fast? Am I going too slow? Am I good? Yes? Okay, cool.
You're doing good.
Wait. Can you tell me how did went backward? Shouldn't it be going up?
Right. So that's what negative r values mean, right? If it was 5 comma pi over 4, that means I would go pi over 4 and then go out 5 units. So that right there would be 5 comma pi over 4. But since it's -5, I have to go in the opposite direction.
So do you have to? Okay, I got it. Okay.
Got it? So the angle, so the angle measurement is going to determine the direction, essentially, right? If I had said, what is that? What's pi over 4 plus pi? That's 5 pi over 4, right?
Yeah.
So if I said 5 pi over 4, right? And then with a -5, that's actually the same as this guy, right? This would be -5 pi over 4. You see that? Because this is 5 pi over 4. And then I want to shoot the other way, so it's like I got to put a negative on it. Is that all right?
Okay.
You guys,
Yeah.
you guys understand that? Yeah. So hopefully it kind of builds this intuition that like there are an infinite amount of ways to get to a single point. Kind of like if you guys have ever seen like those movies with like submarines in it and like you see like the radar go like beep, 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 right?
Yeah.
You can essentially sweep as many times as you want, right? You can sweep as many times as you want and still get to the same point if you wanted to. So like if on a midterm, wink, wink, right? If on a midterm, I'm like, get to this point, but give me a negative R value and a positive R value, you should be able to get there. You see what I'm saying? Right? Okay.
Yeah.
All right. I winked at you guys, okay? So just remember that. All right. So that's good. We talked about that. I'm going to ask China to do,
John,
I'm
I
running
have
out of time here.
a question.
Oh, yeah. What's up?
So in this case, if you're given an angle, is it possible to have 2 R values?
Yes.
Because if your function
That's what I'm saying. Yep. So
right.
like you notice how this point right here had 2 R values, 2 theta values, but you still ended up at the same point. Right?
Yeah.
I can give you can someone give me a third point that's different from the first 2? That still
You can
ends
add
up,
360. You can add 2 pi.
you can add 2 pi to your to the theta, right? So that would be like you can go. I'm gonna go with this one. So 9 pi over 4. So that means
you could do
I go
-9
around.
pi over 4.
Or
Yeah,
negative
it
9
would
pi, right? And then same thing, 5. And boom, I'll get there again, right? Can you guys imagine the rotation? Yeah. Okay.
Okay.
I'm gonna ask China to do the converting points with you guys because that is going to be on the midterm. Converting rectangular to polar, and then like going backwards too. But this will be covered by China. So this means we can go from rectangular to polar and polar to rectangular, but we need some conversion factors, right? We need something to kind of like change the X's into R's or whatever, like X's and Y's into R's and theta.
Trigonometry.
And it all actually comes from trigonometry. I'm going to give you guys the conversion factors right now. So The first one, you guys should know this one, x squared plus y squared is equal to r squared, right? That's just the equation of a circle. And we know that this holds true in math because that's, once again, that's the equation of a circle, right? But we can also use this to find our r values, right? If this is true, then we can say r is square root of x squared plus y squared, right? So if I give you an x and a y, you should be able to tell me an r, a corresponding r, right? The next two conversion factors come from trig, and they should look familiar. Cos theta is x over r. Does that look familiar? I hope so.
Yeah.
That's
So
this is from the
it's just a bunch of unit circle stuff.
yeah. This is from the unit circle. Like
Yeah.
right, if like my radius is 1 because it's a unit circle, you remember cosine represents x and sine represents y. Tangent is y over x, right? That's where all that stuff comes from. So this can be r cos theta is x, right? So if I have an r and a theta, I can plug it in and get the x value. So, so I'll write here, this is good for pole to rect, get rect, right? And then similarly, you're gonna get, oh gosh, r times sine theta is y. And this also is good for polar, oh my gosh, polar to rectangular. This one, the first one is good for rectangular to polar. And one more for good measure, tangent of theta is equal to y over x. This is to figure out, right? This is to figure out theta. There you go. So this is good for rectangular to polar, right? Because I can just tan inverse and solve for theta. Okay, so I'll have China do an example with you guys with this stuff, all right? Because I need to move on to the more complicated stuff. Oh man, okay. Why don't
John?
I show, yeah.
So you said the rest of this, we're gonna go over examples with China, right?
You're gonna, just with converting points, because I'm gonna move on to converting functions, because we're.
Okay, so will this
wanted to-
also be on the midterm?
Yep.
Okay.
So yes, these conversion factors are very, very important. You need to know them. You need to know them, know how to use them, right? Okay, so yes, like I said, we can use these to convert points, but we can also use these to convert functions, all right? So why don't I, oh my gosh, I still haven't even shown you guys polar graph yet, right? So why don't I do this? I'm gonna show you a polar graph and
Make it real trippy.
no, not yet. You guys aren't ready for that. So yeah, I'm gonna start off with an easy one. Okay, a times cos theta. I'm not gonna require you guys to memorize like the parent functions, like parent polar functions, but you will probably need to know them in the fall. I'm just letting you know. Okay. Most likely, if I give you a polar example, if it's a complicated one, I'm just gonna give you the graph. All right, but there might be a wink, wink. There might be a question where I give you a simple polar graph like the one I'm showing you right now, and you have to kind of sketch it or describe it. Okay, I hope you guys saw that. The wink. I winked. Okay, all right. So the first example I'm going to show you is r equals a cos theta. So it's a is just a constant, and watch what happens when I hit the play button on this. Can anyone describe with words what's going on?
That if the negative, it's gonna be on the second and third quadrants.
Mm-hmm.
It's positive, it's gonna
At the
be
left
on the
side,
first
okay.
and fourths. Yeah.
And then if it's positive, it's on the right side, right?
Yeah.
Do you guys remember the relationship between cosine and, like, we kind of just said it before, cosine and the rectangular plane? What was the relationship?
I remember. Yeah, I know.
I
But
just no, I just
code.
cosine
X
represents
over R.
what?
X over R.
X. Cosine is related to x.
Oh, yeah.
So depending on the value of what the heck? Sorry. Some people are like dropping in and out. So depending on the value of a, it's either going to expand to the right. Wait, is this right for you guys? Or is this left? Is this right? Whatever.
Yeah, that's right.
Yeah.
That's right. Yeah.
This is going to expand if the a value is positive, it's going to be a circle that expands out to the right, or a circle that expands out to the left if the a value is negative. Do you see how that works?
Yeah.
More
Yeah.
specifically, if you pay attention, if I have an a value of 1, what do you notice is the radius of
I was
the
gonna say
circle?
that the larger the
becomes
absolute
small.
value, the larger the circle.
The
Or the A
larger
value.
the a
The
value,
absolute
the
value
larger.
of the A.
Yes.
Yeah.
Yep. Okay, but pay attention more closely to the
Oh,
value
so
of a.
The radius
so
is
the
1. The
radius
radius
depends
is
on
a
the
con.
value of a.
Oh, was it who was that? Shubham? I heard you.
Yeah.
Yeah. So the radius depends on is pretty much going to be I don't know if it's a or
A,
right, because if it's 4, that means it should be 2, right? Yeah.
yeah,
So
yeah,
yeah,
it's
the
A over
radius.
2.
Yeah, the radius is going to be a over 2. Does that make sense?
Yeah.
Okay.
Yeah.
So take a guess. What do you guys think is going to happen if I turn this sine one on?
I think it's going to be like the opposite of what happened to
Be careful
cosine.
when you use that word opposite in math, because that can mean a lot of things.
Okay. I feel like when it grows, it's going to grow on the right chord on the when it's positive. When it's
Remember,
But-
cosine represented what?
X.
Oh, so it's gonna be
X.
going up and down the x-axis.
First.
Yes.
Oh yeah, it's gonna
Yeah.
be up and down.
First
Yeah.
and second.
Yes. Right. Watch. I just turned it on. I'm gonna hit play. Right. It expands upwards, and then when it goes to the negative, it expands downwards.
Cool.
Same rules apply. The radius is gonna be a over 2, or I guess in this case b over 2. Right. But then we can get some really trippy looking functions. So these can create like they're called cardioids. They have like so many different like Latin names or whatever, or French names. There's one called like lemnis Scotti or something like that. It's like the infinity sign. So there's some really trippy functions you can get. There's one where like if C and D in this example, if the ratio is 1, it creates this figure which is called a cardioid, which means like heart, like a heart shape. I call it the butt shape because it looks like a butt, right? But if you notice, if I change like values, I can kind of like see that, see what's going to happen to the graph, right? It flips it in a certain way. Like, what do you guys think would happen if it was sine instead? What happens if I mess with the C value, right? You notice it gets bigger or smaller. So it's like, I'm not going to ask you guys to memorize these graphs, but they might ask you to memorize them for the fall. Okay, these are some of the graphs you're going to come across, and that are the most common in calc, right? So let me stop that for now.
Dang, that was trippy.
Oh, trust me, they get even. Think about what's going to happen when you throw a tangent in there.
And that's where I leave the call.
It's like the graphs like doing all of that. It's crazy. All right. So here we go. We're gonna convert some functions into and kind of prove that like they are what they are. What do I mean by that? I get it. R like radio. So example 2. Let's look at an easy one. This is on page 656 in the textbook. So if I have a function r equals 2, oh, I don't like this example. Yeah, whatever. Okay, fine. A cos theta, and A is it's a positive constant. So A is just it's just a number. So I'm not changing a point into I'm sorry, I'm not changing a polar point into rectangular now. I'm changing a whole entire function, okay? I want to be able to represent this on the rectangular plane. You know what I'm saying? But I can't do that right now the way it is, right? Like I need to understand what this is in terms of X's and Y's to kind of see the picture. You guys get what I'm saying?
Yeah.
So what do you guys think? Can someone throw out an idea? How are we going to use these conversion factors to kind of like get this to look like something with X's and Y's?
I think we should do the x squared. You know.
Could we maybe solve the whole thing for cosine theta, and then like look
Good
at your
guess.
x?
It's a good guess, but remember it has to be r cosine theta to be an X, right? So it needs an R.
So then do you just divide by 2?
I mean, we could.
Oh wait,
Wait, so is
could
it gonna
you-
be cos
Oh, wait, hold
cos
on.
theta divided
sorry.
by 2a?
I mean, we could if you want to. I
Could
don't think
you-
that's gonna help us though.
Could you divide the whole thing by sine to make it cosine or cosine over sine? That's cotangent. Never mind.
Yeah,
I was
no,
thinking
that's adding fuel to the fire.
my bad.
Anyone else? I know
Wait,
it's
is it gonna be is it gonna be cos theta divided by 2a?
No, I mean that's not really gonna help us though, because like think about it. If we need an r with the cosine, and we know that if we have r squared, we get x and y's. Do you see what I'm saying? So that means what I can do is
Multiply by
multiply
by
both sides by
r.
r. Right? I know it's a pretty it's a tricky solution. I know it's you wouldn't have thought of it, you know, but it's okay. Now you know, right? So if I multiply both sides by r, you get r squared equals 2ar cosine. And now we can do some substitution, right? We get r squared is x squared plus y squared is equal to 2a r cos theta. Well, we said that's the definition of x, right? And now I have something in terms of x's and y's. I just need to figure out how to get from here to something that I can interpret, right? So watch what I'm gonna do. I'm gonna say something that might make you guys upset, but I'm gonna move this over. Can anyone see what I'm gonna try to do here?
Yeah, it's the a
Like make it
square
factorial?
plus 2ab plus b squared equation.
Yeah, what's that called, man? Do you remember what that's called? I need to do something. I need to complete.
Complete the square.
Yeah, if you guys don't remember, there's something called complete the square.
Yeah.
Wait, but that's quadratics, right?
What's that?
Isn't that quadratics?
Yeah.
Oh, okay, never mind.
Well, we have kind of a quadratic here, right, with the x squared. We need to complete the square to kind of tell us where the center of the circle is. Can you guys see that this is a circle yet or no?
No, yeah.
It's like an x squared and a y squared being thrown around, right? So it has to be a circle. So if you guys don't remember completing the square, cut it in half and square it next. You guys learn the jingle? No, they don't do that anymore, right? Plus, so you cut the b term in half.
Wait, so what's the jingle?
Wait, what's the jingle?
No, you guys aren't going to trick me into saying it for you.
No, because I'm curious now. You
Yeah,
can't
okay.
do that.
You're going to divide the b term by 2 and square it. So that ends up being a squared. Right?
Yeah.
Because
And then subtract the square.
b term. And then not subtract, we got to, since we did it on one side, we got to add it to the other side. Okay? Maybe?
Yeah.
All right. So one example. Okay, cool. I'm doing this right. All right. So then we get x squared minus a. I'm sorry, x minus a quantity squared. Plus y squared is equal to a squared. No? No, this is
Yeah.
supposed to be the part where you
Yeah.
guys go,
Yeah.
"Oh
I
snap,
understand.
that's a circle where
Yeah,
the
I
center
understand.
is a comma 0," and isn't that what we just said? The center is it's going to expand out that way, and that's a. No,
Yeah.
we just
And
proved it
the
algebraically.
equation of the circle.
No, okay, all right. I tried. You know, I
I'm
tried.
sorry,
No, we
algebra is still
understand.
like
Yeah. I know. Who needs algebra when you got calc, right?
facts.
All right. So, there will be a question where I ask you to convert like an equation from either polar to rect or rectangular to polar. So keep an eye out for that. Okay. Oh my gosh, I only have 10 minutes left. Are you kidding me? Oh my gosh, this sucks. All right. We got to move on to the next section. All right. So 11.3 was kind of like an intro to polar coordinates. You know, how to play with them algebraically, how to convert, how to put like what they look like on the coordinate plane. But 11.4 now is where the calc part comes in. Now we're going to start introducing calc ideas with polar coordinates. Now, I'm going to skip the differential part of polar coordinates. It is kind of interesting. You know, you can take the first and second derivatives and blah, blah, blah. I'm going to focus more on the area part because this is usually the part that is a little bit more confusing or like, you know, harder to like kind of picture and stuff. So we're gonna talk about 11.4, which is area and arc length. I may have to just kind of skip arc length. I don't know with polar coordinates. I haven't decided yet. Okay, so arc length, that's why I kind of highlighted it before. I might skip it. I'll let you guys know. But area for sure. I want you guys to understand how the area part works. Okay, it's an integral part of this class. Okay.
Nice.
Mathematics joke.
All right. Okay, so if you remember, finding the area under a curve, right? We need to sum up an infinite amount of cross sections. That was like the big theme of chapter 6, right? But in this case, you know, when you have polar graphs, especially ones that are like all like squiggly and stuff, you know, and like they don't look like normal or like functions that you're used to, we have to do something else. We're not going to use Riemann sums anymore. They're not called Riemann sums, all right? We actually have to use different shaped cross sections. Still with me?
Yeah.
So what does that mean? If I kind of draw it out here, if I wanted to pick, let's say this point right here, I would need to go a certain theta. I'll call it theta 1. And then the function would tell me what r length it would be, right?
Yeah.
And then if I wanted to maybe find this next point, because let's say the graph is moving in that direction, right? Like that's usually denoted by like this. But if the graph is like kind of being drawn in that direction, I would need a second theta. I'll call it theta 2, and it would output a second r value. Does that make sense?
Yes.
Yeah.
Still with me? Well, if I wanted to shade like this piece right here, if I wanted to find the area, that means that this from theta 1 to theta 2, I would need that to become very, 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 very small, right? Kind of like with the thin rectangles, how you guys learned integrals, right? I would need them to become very, very, very small. And if you can kind of picture that, I'll reach, I don't want to redraw this. If you can kind of picture that, right? A very, very, very small piece ends up looking like something that you guys have learned in the past. Anyone want to take a guess at what that is? We don't have time for it. It's a sector. What we just found here is a sector. And I don't know if you guys remember sectors, but it deals with circles, right? It's like if I ask for like the area of that, right? No, maybe.
Yeah, I remember. Yeah, geometry.
Yeah. You learned this in geometry, pre-calc, or whatever, but you learned the area of a sector. It's 1/2 r squared theta, and theta has to be in radians.
Mm-hmm.
And what does that mean? It kind of changes our area formula, like what needs to go in the integral. right? It changes what needs to go in the integral, right? So we have to integrate our area function. In this case, it's our sector. And hopefully you guys can see like, chapter 6 kind of coming back, right? Because it's a very fundamental idea here, right? So we have to integrate the area of the sector an infinite amount of times from 1 theta to the next. But what are we integrating here? We need a function, right? We need our R function in terms of theta, right? Because that's where this one comes from. And we need to square it along with the 1/2. And instead of theta, right, it's not going to be like a constant theta amount. It's actually going to end up being really, really thin pieces of theta. That's where the d theta comes from. So it has to be d theta. Do you see how I did that? Like I just took the area formula and just kind of like put it into an integral.
Yeah.
Is that all right? You guys okay?
Yep.
Okay. So like if I had
I have a quick question.
I
Is
have
that
a
theta
question.
squared?
oh, yeah, what?
Is that theta squared? Yeah.
The theta
the
is
R
not
and the-
squared. The theta is not squared. It's the function.
Okay.
F of theta. Your R is squared. Your R function is squared.
Okay.
Right. If I kind of go back, right. In this example right here, R is a function of theta. My input is a theta. It's going to output an R. Right.
Okay.
So it's the same thing here, right? I could have written this as F of theta too, because technically it's a function of theta. We just set it equal to R because we know R represents radial length. How we doing? We okay?
Yep.
You guys
Yeah.
lost? No?
Yep.
In the book, they go through some examples with finding area with polar graphs. So it gets a little tricky. I don't know if I should give you guys the easy one first, or let's just do the easy one. And if I guess China can do the harder one. So here we go. Example 1. This is on page 663 in the PDF. So it says R equals 4 sine theta, right? This is going to be a circle that's expanded upwards with a radius of 2. And it's saying to find the area of the right semicircle. Oops. Now, do you have to use the formula with the polar stuff? No, we know how to find half of the area of a circle, but if it were a more complicated function, then we have to do it this way, right? Does that make sense? Right. So yes, we know it's a circle with a radius of 2, and we could just use pi r squared and cut it in half if we wanted to, but instead we're going to show it using the integral stuff that we just learned. So the formula, once again, it's 1/2 theta 1 to theta 2 of, let me write the general one first. R squared d theta. So what you're gonna notice is, you know what? I'll just wait. I'll wait for the grade reveal. You have to figure out the bounds. Okay, so this is probably like the hardest part of these types of problems, because like I said, it's a circle that expands upwards. Pretend it's a circle. It expands upwards, and we have to figure out this from here to here. Okay. So the way you kind of figure that out is just kind of plug in some values. You know that when you plug in pi over, I don't know, 4 into sine, you're going to get a positive radial length, right? So it's like, it's actually going to be like somewhere like there. That's going to be, I don't know what the radial length off the top of my head. It's going to be, what is it? Root 2 over 2. But then you got a times of 4, so it's going to be 2 root 2. It should be, so 2 root 2 comma pi over 4. Right? That's this point right here. So you can tell that the circle is being generated this way. Right?
Yeah.
And then you know that this point has to be pi over 2, because if you plug pi over 2 into the function, into 4 sine theta, right? R of pi over 2 is equal to 4 times what's sine of pi over 2? That's 1. So it's just 4. You see how we got there?
Yeah.
So that means my bounds are from
Can you
0
explain that again?
to pi over 2.
Can you
What
explain
part?
that?
What
Like the one, how you find the coordinates, how you get.
Oh, so I'm kind of like plugging in easy trig values that I know, right? This is why trig was so important. Like I first tested this. I plugged pi over 4 into my function. I got 4 sine of pi over 4. And that ended up being 2 root 2, like a positive R value. So I know that like the cannonball is being shot out here, like out there, right? And then I tested pi over 2. I got 4. So that like told me the circle is being generated like in that direction.
So basically, whatever's like the highest number you produce is is like one of the integrals, or no?
Well, the question was asking for the right semicircle, right? I know since it's a circle, we could have found the left and it would have been the same thing, but we specifically wanted this right half. So we need to pay attention to which direction the function is like sweeping, if that makes sense.
Okay.
Yeah? So we need to pay attention. Is the function sweeping this way? Is the function sweeping this way? Is there a negative value? So are things going backwards? I know it's kind of a lot to kind of keep in mind, but yeah. So that's why I'm going to keep the problems like relatively simple for you guys, right? So okay, so we have our bounds, right? We have our bounds. We know our function. Let's do this thing. So we go 4 sine theta. That's going to be squared d theta.
Is the half on the outside too?
Oh shoot! Good looks. Good looks. There's 1/2 on the outside. And now we have an integral that hopefully you guys can integrate. I'll rewrite it here. So 1/2 integral from 0 to pi over 2, 4 sine theta, quantity squared, d theta. Let me simplify a little bit here. It looks like an 8's going to be on the outside. Sine squared theta d theta. And we hit a roadblock. Maybe. Anyone? Anyone know?
Wait, John, why is it 8 on the outside?
You square
the
4,
14,
you get
pull it out.
16.
Oh, yeah,
over
okay.
2.
Sorry, my bad.
No worries, no worries.
Can't
Oh my
you
gosh,
do
I'm
the-
so over time. Okay, I'm just gonna tell you guys, this you cannot integrate with normal methods. You can't use U sub, you can't use integration by parts, blah, blah, blah. So we need something that you guys learned, but most likely forgot. You guys remember? Anyone?
Is it gonna be? I don't remember. No, 1 minus cosine squared.
Yeah. Oh no.
Their identities?
Oh,
It's gonna be 1 time.
No.
Sine.
It's not the trig identities. It's your
Half angle formula?
half angle
God.
formulas.
Oh.
Yes, you
That's
must
good.
know them. They are very,
Oh,
very,
God.
very important, especially for polar stuff. Especially for polar stuff, because you
What's
can't
that,
integrate
though?
this. You can't integrate that the way it is. You don't know what the integral of that is, right? So we have to use our half angle formula. So this becomes, I'm so sorry I'm running over time. This becomes 1/2 times 1 minus cos 2 theta. D theta. Oh, okay. Right? Do you understand, right? Like, because of that squared, we couldn't integrate it. But if you look, that half angle formula gives us something without a square. I know how to or hopefully we know how to integrate cosine of 2 theta. Hopefully. Right? So this becomes 4 integral of this, 1 minus cos 2 theta. For time's sake, I'm sorry, but I won't be able to finish this. You guys can finish this on your own, hopefully. Yes. 1 becomes theta. You got to take out the 2 and do the cos 2 theta. All right. I did not get to a lot of stuff, so I'm gonna do more examples of like this in the video, and then have China do a couple during recitation. But really, I wanted China to focus more on the midterm. So I guess this is going to be kind of part of it too. Then, if anyone wants to stick around, you can for a little bit. Ask me any questions, but you guys can go to your next class. Be on the lookout for the supplemental video. All right.
John, I'm going to subscribe this time. I promise.
What's up?
I'm going to subscribe this time. I promise.
Oh, okay. All right. You better.
Are you gonna post the solution for the quiz, or are you guys gonna?
You know, that's a good idea. I will, but only until everyone has taken it.
Oh, okay.
All right.
All right. Thank you.
Yep.
John, I had two questions.
Thank you, John.
Yep. Anytime. See you guys on Monday.
John, I had two questions.
Yeah.
The first one, if you could scroll up a little bit to like the circle, like the semicircle one.
Semicircle. Yeah.
Yeah, right there. So you know how it's on the on the y-axis?
Yeah.
Will it always be like that, or will it be about a different axis in other examples? Like if they said semicircle, like could they say on x equals whatever or y equals whatever, if that makes sense? I don't know if you're getting what I'm trying to say.
Are you saying like if there was another?
Like if this same semicircle but was
Axis?
plotted on like
I
x
think what
equals
he's
2.
trying to say. I think what he's trying to say is like, you know how it has sine, so it's on the y-axis. If it has cosine, it's gonna be on x-axis.
Mm-hmm.
I think that's what he's trying to ask. Like,
I
can
guess
it
what
be
I'm
in
trying to say is
x-axis or
like
no?
if it's sine and cosine, it's always on either the y and x axis. Like that's it. That's the term we'll see.
If it's in the forms, like I said, there are a ton of like polar like graphs that are like considered like parent, you know.
Mhm.
But if they have the form this or this, it's either going to be expanded out positively on the x or
Okay, all right.
negatively on the x or positively on the y, negatively on the y, depending
So
on.
it's possible to have it go like instead of the y-axis, it's going to be like x equals 3 or something like that.
I mean, yeah, that just means the circle is going to be centered at 3, right?
Yeah. Okay. That's like weird.
The other question was in 11.1.
Yeah.
I mean 11.3. Sorry.
11.3. Yep.
The first example. Why was it 5 pi over 4 when you drew like the circular motion? If that makes sense.
This one, this example.
Yeah. Why was it 5 pi over 4? You see the arc you drew.
Is it not 5 pi over 4? Yeah, pi over 4 past pi is 5 pi over 4. Yeah.
Oh. Okay.
Well, I'm saying
I
like that's pi, right? If I go that much. Well, if I go pi over 4 more, that's gonna be like.
Oh yeah, it's 5 pi. Yep, makes sense. Okay, got you. Thank
John,
you.
I have a question.
Yeah.
For the exercise that we did, the last thing, 11.4.
Yep.
You found your bounds to be 0 to pi over 2, right?
Mm-hmm.
But like, how'd you find 0? Like, I know that you can see it in the graph, but like, how would you find your lower bound?
Well, try plugging in 0. What do you get when you plug 0? An angle measurement of 0 into your function. You get 0.
Also, your bounds are like the smallest and biggest value you can get. Is that what your bounds are?
The way we choose our bounds is determined by what section we're trying to find. You know what I'm saying? So like, if instead the problem was like, I don't know, let me write down here. If instead the problem was like, find this area, our bounds need to be different. We would need to go like from like here to here.
You can't assume that the circle half is always going to be like the same circle half. Like you always have to do the one that they ask you.
The only reason I did circle was because I thought it was gonna like it's an easier like picture. But if you have something like, oh gosh, sorry.
No. It's like the devil's logo.
If I have something like that, like and they say like find me the piece in the 4th quadrant, you know? Like you have to figure out, well, what is this theta value? And then what is this theta value?
Oh, got you.
So it depends on like the complexity of your graph and like what section of the graph you're looking for. In the video that I'm gonna post, I'm gonna do a problem where it's like when you have embedded polar functions. Something like this. If I have a cardioid and like a circle that overlap, okay, like how do I find the area of the stuff outside the butt cheeks? Like right there. You know what I mean?
It's a beautiful picture.
Yeah, thank you. So we need to figure out like the theta like stuff that works and all that stuff. But definitely check out the video for that.
Okay.
Right.
Hey, John, have a good one.
You too, man. Take care. Anyone else? Issues?
Yeah, can you go up a bit, like on 11.4?
To where?
Right there, right there. So scroll down a bit. There you go. Okay, so you know how you see that pi over 4, right? R pi over 4 equal to 4 sine pi over 4 equal to 2
Yep.
square root of 2.
Yep.
Was it part of the graph or no?
What do you mean, was it part of the graph?
Like, you know how you solved it for like pi over 2, R pi over 2 equal to 4? Was it part of that?
Yeah, so the reason I did these, right? The reason I did that was to tell me what direction the graph was being graphed in. Like, so these two things tell me that when I generate the graph, it's going to generate like this. It's going to like go, it's like going in this direction. Do you see what I'm saying?
Yeah.
As opposed to going in the other direction.
Okay.
And that's an important factor to consider when you're.
Because then you'll have to start using negatives and everything.
Yeah. If it generated the other way, then like we would have to go from pi over 2 to pi.
Thank you, John.
So,
have a good weekend.
All right, you too.
So pi over 4 wasn't part of the thing. 1/2 integral 0 to pi over 2, that equation.
No. So these were kind of like I guess they were kind of like test points.
Okay.
Right. I tested some points to see which direction the graph was going to be generated.
Okay.
And I picked easy. Right. I didn't pick like pi over 7. Right. Like I picked easy trig like values that I knew so that I could compute it easier.
Okay. Got it. Thank you.
Yep. Anytime, man.
Have a good day.
You too, man. Actually, Lamek, stick around. I wanted to chat with you a little bit afterwards. Harry, what's up?
So, in the case of the cardioid, like you showed in the last example, we wouldn't be able to tell if it was moving counterclockwise or clockwise. So, you'd have to. How would you choose your bounds?
Oh, there's you're talking about this one, right?
Yeah.
Yeah. I apologize for the crudeness of the picture, but you have to do since okay. So you remember like when we had two regular functions in the coordinate, xy, we did top minus bottom.
Mm-hmm.
We have to do something similar. We have to do something. It's called and like I said, I'm going to do this in the video. Outer minus inner. With like polar coordinates. So I'm gonna do this.
Since that's symmetrical, so let's multiply by 2 and then you
have to find the area of the half semicircle and then subtract the butt cheeks.
Okay.
You get what I'm saying? To get the green. To get solely the I'll mark it in blue. To get just the blue. Do you get what I'm saying? So that's the idea. You got to do an outer like polar graph minus the inner polar graph, and then which means you have to figure out like the bounds like that create like the butt cheeks versus the half semicircle.
Okay.
Right. But like I said, I'll put it in the video, so check out the video.
And do you think we could go over a question on the quiz, or not yet?
Which one?
It was the improper integral, number 3.
Okay. Like what part of it?
Well, you just had to solve for it. They gave you the bounds and the formula.
Mm-hmm.
Do you want me to tell you it or?
No, I have it here, but like you want to see the whole thing?
Yeah, just like the process.
All right, so I'm not going to do the whole thing, but so what method did you use to integrate this?
Well, I think this would be by parts, wouldn't it?
Yeah. So you set your u as x, and then your dv as e to the negative 2x.
Oh, you use tabular?
Well, yeah, because one of them is a power function.
Okay.
So when one of them is a power function and the other one is an exponential or trig, you can use tabular. Or you can also do it by parts. You're just gonna have to do it twice.
Okay.
All right. So this becomes negative 1/2 e to the negative 2x. This becomes plus 1/4 e to the negative 2x. Plus minus. This becomes negative x over 2 e to the negative 2x minus 1/4 e to the negative 2x, and we're going from 1 to r. Limit as r goes to infinity.
Okay.
Can you take it from there?
Yeah. Yeah, I got it from there.
Okay, cool.
And if you have time, could we also do number 4? That's the last question I had.
Is that the differential equation one?
Yeah.
Okay, yeah, so I'm not gonna do the whole thing, but I'll do part of it. So y cubed, y prime, minus 9x squared equals 0. So you separated the variables. You get y cubed dy equals 9x squared dx. And you just integrate both sides. Getting you y to the 4th over 4, which is 3x cubed plus c. The initial condition was 1, 2. So you plug that in there and you just solve for y. I'm sorry,
Okay.
you solve for c and then you solve for y.
Okay.
All right.
All right, sorry.
No worries. Just Harry, if you had, I would have been able to get through these questions because I don't want you to be late for your next class. And if you wanted to do this, we should have done it in the beginning because that's why I sent that text. I was like available at like 12:40.
Yeah, I was with my little brother. I had to do something with him. That's why.
Okay. Yeah.
But
No worries.
but yeah, thank you for going
Yeah.
over with it.
Anytime, man.
All right, have
I'll
a
see
good
you
one.
Monday. Bye. Hey, Lamek. So I just wanted to let you know that I decided to not give you a 0 on the first one, on this first quiz. I was kind of like on the border, like whether or not I should do that. But like I said, I trust you. I know that you're a responsible guy. I love your participation in class. So I just decided to just bring the whatever you get. I'm just gonna bring it down a letter. Is that fair? I can't hear you.
That's more than fair.
Okay.
Thank you.
Yeah, man. I just wanted to let you know. Okay.
Thank you.
All right.
I just wanted to say, I just wanted to say I'm sorry again. I wanted to actually
It's fine.
apologize in person because like over text and everything. Yeah. Thank you again.
Yeah, man. All right. I'll see you on Monday. Okay.
Yeah.
All right. See you.